All right, welcome everybody. Good to see you. Welcome to Unit 3, Lesson 7. As usual, you're looking for the tasks to complete for U3L7. You can find it under assignments or on the Canvas homepage of the weekly calendar. Today's date is December 3rd. Rather than putting you into breakout rooms to chat about a question, we're going to start off today with a feedback survey. I meant to do this earlier, so I apologize for not getting this from you sooner. But there is an anonymous Google form that link right there on the Do Now, the very first thing. So I'm going to give you 10 minutes to complete that. It's just some questions about what you've been liking and not liking about the class so far, specifically the tools we've been using, as well as just how you feel in general. So everything's anonymous. I really appreciate honest feedback, and I'll do my best to respond to it accordingly. So take 10 minutes to fill this out. Hopefully it won't take 10 minutes, but we'll come back together once most people have completed it. So 10 minutes for the feedback survey. Temperature, and it looks like 6 of you went with A, the boiling temperature would not change, and 5 of you went with C, the boiling temperature would increase. And so the correct answer is indeed A, the boiling temperature would not change. Assuming you're at sea level, does anyone know what temperature it would stop at? Like no matter how much you heated it, the water is always going to be at what? Does anyone know at sea level for boiling in Celsius? It's a nice round number.
100 degrees.
Yeah. And so no matter how much you heat that water, it will stay at 100 degrees Celsius, which I know is weird, right? Because again, so don't feel bad. If you went with C, the boiling temperature increases. That is a very common misconception. That's what a lot of people think. But there's some interesting stuff going on here on a molecular level, and that's what we're going to explore today using a couple different things. So more on that in a bit. Homework was looking great. You had to finish the PhET simulation worksheet on states of matter. We got most of this done in class, if I remember correctly, but it looks like most of you were also able to finish this outside of class. Homework, which was Hewitt chapter 11.2 and 11.3 on states of matter, also looking good. I'm seeing 13 attempts on this one. I am seeing a couple questions where we've got 1 or 2 people choosing wrong answers, and I just want to remind you that you can retake this quiz to correct any mistakes to get that perfect score. So I encourage you to do that. If you got points off, you can always go back. It will also, Canvas will tell you which questions you got wrong, so you know which ones to focus on. Any questions or comments on those homework assignments or anything you needed help with? Okay. So we're going to start off today then with an activity that relates directly to that formative assessment probe. If we were on campus, we would have actually done this experiment where you're going to create what's called the heating curve of water. Just going to share my screen again really quickly. Here's what we would have done if we were on campus in the laboratory. You would have taken a beaker, we would have put ice in it, and stuck a thermometer in, and then stuck it on a hot plate. So kind of very similar situation to what you were seeing in that formative assessment probe. And we would have turned on the hot plate and basically melted the ice and then brought the water to a boil, and you would have recorded the temperature over time, like every minute for like half an hour or something like that, which I know doesn't sound very exciting, but it yields pretty interesting data. Anyway, unfortunately, I can't expect you to do this at home. I know not everyone has thermometers. So instead, what I have done is created a Google Sheet with data from previous years. And all you need to do is graph it and then answer some questions in a little kind of Google quiz thing related to the graph. So there's the data. As usual, I have instructions. You need to make your own copy, put your last name as the first part of the title, get the shareable link that you'll then post as your answer to that first question, and create the graph. And then once you have the graph made, you can go through and answer the questions, and we'll review this once everyone is done with it. I'm going to time for 15 minutes. I'll be here if you have questions or if you're not sure what to do. But otherwise, 15 minutes to work on the heating curve of water quiz and graph. Go for it. Let me know if you need help. our review. Any questions or comments on that activity or quiz?
It's not a question or anything. I
Mhm.
don't know if it's me, but there's like a squeaking noise
Oh,
when you move the
might be me.
screen. Does anybody else hear that?
Are you hearing it right now, though?
No.
Okay, it might be me. I think there's a part of this desk. I have my computer on like a metal stand that seems to be squeaking. So I will try not to lean on it or anything. But Sophie, let me know if you hear it again. I'm
Oh, I
just
wasn't. It didn't bother me or anything. I just wanted to let you know.
okay. It's a secret sound that keeps you all awake, right? That's what I'm doing is transmitting it through the computer. So all right, no. Well, again, let me know if you do hear it again. We'll try to track down the source. Okay. All right, you kids ready to be guinea pigs? Going to try out something here. Next thing I'd like to do is, again, a quick review using slides and questions. But rather than using Google Slides and poll questions, I want to try using a program called Nearpod. So on tasks to complete step number 5, go ahead and click on that first link there, Nearpod vapor pressure and boiling point. It should take you to a sort of joining screen where you have to enter a join code, kind of like you would do with Kahoot or something like that. I'm going to pull up the join code right now. This Nearpod program is kind of like Edpuzzle, but for slides, and I'm still kind of new to it, so bear with me. Might be a couple snafus, but we'll work through them. Takes a little while to load, so we'll give it a minute. All right, there's our join code. So when you click on that link and ask for the code, you should enter ET6UB. I threw the join code into the chat on Zoom as well. And you can always see it in the upper left corner of the screen, kind of like with the Kahoot again. All right, looks like we got 4 people joined. As with Kahoot, please use your name or something close to it. There are 12 of us here, so I'll wait to get to 12 or close to it. All right, we're at 11. Since most of us are on, I'm going to go ahead and start. But again, for our last straggler, you can always see the join code in the chat or in the upper left corner. Here we go. All right, so we're picking up where we left off with the states of matter. Going to go into a little more detail now about what's happening on a kinetic level. But again, if you ever get lost, just remember we're talking about the transition from solid to liquid to gas, right? That's where we're adding more kinetic energy. We're making things really excited and energetic going this way. Or reverse, where energy is being released or removed, and you're calming down the particles, reducing the kinetic energy. So the correct answer to the formative assessment probe you took at the beginning of class is indeed A. If you were to bring water to a boil and continually heat it, it would not change its temperature. It would remain at 100 degrees Celsius. And that's because once you hit that point, vaporization occurs. And any more energy that you add doesn't go to changing the temperature, it goes to creating the gas, the water vapor. The only way that you would be able to measure a temperature higher than 100 degrees Celsius is if you took the temperature of the actual water vapor coming off of the surface of the water, which is really hard to do because it dissipates in the air really quickly and cools down really rapidly too, which is why you get condensation around your stove and things like that. Let's explore what's going on here. So here's a cleaner version of the graph that you made using the data that I provided to you. And again, just to emphasize, we've got heat being added on the bottom. So we're continually heating our substance. This is water, again, H2O, that this is showing. and you've got temperature on the side. So we're seeing the temperature change, and not surprisingly, as you heat the solid, so if you're heating up ice, it will warm up and warm up and warm up, but then you hit this sort of flat point, and that is where, at 0 degrees Celsius, melting is occurring. And so the reason that the temperature doesn't change is because the energy is now going into taking all of those particles that were solid and exciting them enough to become liquid. So you're seeing the actual phase change, right? The solid particles are breaking apart from each other, starting to slide past each other and move around. And only once they're all liquid, so once you have no more solid left, that's when you start to see another temperature increase, because then the liquid particles get more and more excited. And again, you'll hit 100 degrees Celsius at sea level with water. That's the boiling point. And at this point, the temperature again stays at 100 because all the energy is going into converting the liquid particles into gas. They're getting so excited that they shoot off in gaseous form from the water, usually bubbling from the bottom if you're actually boiling on a hot plate or something like that. And so that's why we see these pause points. We actually have a term that we can use to refer to this, and this is the big takeaway from this first part, is latent heat. So if you ever hear that, oh, sorry, one more thing to show you. So this is just a formalized version of the same graph, but I like that they actually label those flat points, right? So they're not just flattening it out so they can write. This is really where you would see a pause in the temperature. And depending on what you're doing, if you're heating, that's where melting is occurring. If you're cooling, that's where freezing is occurring. And just likewise, at 100 degrees Celsius, if you're heating, it's vaporizing. If you're cooling, it'll be condensing at that temperature still, 100 degrees Celsius. So you can go either way on the whether you're heating or cooling. And as I said, the term we use to refer to this is latent heat. So if you ever hear that phrase, I want you to think that this is the energy that's being added right at this zone, right here and right here, where it's not causing a change in temperature. So you're staying at 0 or you're staying at 100. Instead, the energy is used to change the phase. And what that means is you're converting from solid to liquid, or vice versa, from liquid to solid. The energy is being put into that transition, or again, changing the liquid to a gas if you're heating, or a gas back to a liquid if you're condensing. And so that's why we see those pause points in temperature change. The energy is still being used for something, it's just not registering as a temperature change. Again, kind of a weird concept, but an important one to try to wrap your minds around. Okay, I think we're going to try a little quiz activity here. They call this time to climb. It's giving me options here. I guess this is kind of like Kahoot. This is my first time using this, so I'm seeing you all appear as little bears underwater. Didn't know this required join codes separately, but all right, this is just a simple quiz question, so I have no idea what's about to happen. All right, I'm gonna wait until we're close to 12. This looks like it's frozen, but I guess, oh, we got a 10th. Okay, gonna go ahead and hit start. Sorry if someone's getting left out. We'll see what happens here. I'm very curious. So the question is, you place a beaker of liquid water with a thermometer in it in a freezer and watch the temperature change over time. Notice the temperature of the water drops gradually until it reaches 0. It stays for several minutes before dropping lower. What's happening in this pause point? Oh, okay. Whoa. All right, looks like Quinn answered the fastest. Am I able to actually see the question? All right. Okay, kids, I need some feedback from you. What did that look like on your end? Like, did it just present the question and you chose something, or did you have to like do something different?
It was kind of like a who. There was like the
Yeah.
question, and there's like four like
Like
choices.
squares that you
Yeah.
hit?
Then you just choose one. Yeah.
Okay. All right. Okay, that could work well for quizzes that have more than one question. All right, we're going to do that one more time. The next one will have 2 questions in it. Interesting. I don't know if it's worth the wait time to get everyone logged in, but all right. The question should have been like this. So yeah, you place a beaker. So I was just giving you the reverse situation. What happens when you're cooling and it pauses at 0 degrees Celsius? The correct answer was that the energy is going into converting the liquid into solid. So it should have been the little purple thing, or I don't know what options you might have seen. Okay. All right, next thing to cover here is this strange concept of vaporization. This is a catch-all phrase to describe the transition from liquid to gas. Now, I want you to be careful here because you often hear people say, oh, liquid to gas, that's evaporation. Evaporation really has a very specific definition, which is it's vaporization occurring at the surface of a liquid that is not boiling. So in other words, vaporization only happens on the surface of a liquid. It's happening all the time, right? If you have a glass of water on the table, evaporation is occurring. Sweat is also constantly evaporating from your skin, more so when you're working out, right? But that's different from boiling, which is where you have heated the water or whatever substance it is to the point where it has enough kinetic energy to create a gas, and you'll see the bubbles forming at the bottom because that's where the heat source is, right? Your heat's on the bottom, and so it excites those liquid molecules on the bottom so much that they jump into gaseous state and bubble out. You're not, if you're boiling water, you're not creating oxygen and hydrogen gas. You need way more energy for that. You are just creating H2O vapor, which is bubbling up out of the water when it's boiling. So the catch-all phrase for all of that, right, for evaporation and boiling is vaporization. So that's a good term to keep in mind and to use. I know I'm being kind of overly technical here, but that's what we say in science. Interesting little side note in terms of our evolution. Evaporation was a really important evolutionary step for us in terms of our ability to sweat. So your skin is covered in sweat glands, which can release liquid when you're overheated. And the reason this cools you down is because that liquid will eventually evaporate, right? It vaporizes. And as it does that, vaporization is a endothermic process, right? You're taking a liquid and creating a more excited gaseous state. And so it removes or takes away heat from your skin. And you might have noticed this, right? If you're sweaty and suddenly a gust of wind hits you, it increases the evaporation and you get that very cold feeling because as all that water is vaporizing off of your skin, it's removing heat from your skin. And it's a pretty big evolutionary step because if you think about other animals, so we as humans can't necessarily run fast compared to most other animals, but we can run for a long time, right? We can maintain our body temperature, not overheat. That's why we can run marathons. Dogs and cheetahs and things like that can run fast, but only for short periods of time. They actually don't have sweat glands. They overheat very rapidly for that reason. So anyway, I just find that a little interesting biology side note there. Okay. Next important concept. So this is the second of 3 important concepts I want you to take from this lecture is vapor pressure. Vapor pressure is a term we're going to be using a lot from this point forward. And it's defined as the force exerted by a gas above a liquid, which I find very confusing. But if you have a sealed container, right, so here's a liquid, there is a vapor form of that liquid also in that empty space. And those vapor molecules are banging against everything, the glass and the liquid, and that's what you call vapor pressure. But let's put that to the side for now. The definition that I want you to keep in mind from now on is this one in red. Think of vapor pressure as the ability or the likelihood that a liquid will vaporize. So if something has a very high vapor pressure, that means that it is going to turn into a gas very, very easily. Whereas if it has a low vapor pressure, you're going to have to apply a lot of heat, provide a lot of energy to get the liquid to turn into a gas. And so I think what will help clarify this is your experience with existing liquids. So here's a graph that is showing the relationship between 2 things. On the bottom, you've got temperature. So we're heating it up. So we're getting warmer going this way. And on the side, you've got vapor pressure. Again, think of this as the ability to vaporize. So this would be very high vapor pressure, things that become gases very easily. and then down below would be low. Man, I cannot write with this thing at all. So you might notice from the shape of these curves that there is a correlation, right? That the higher the temperature, the more likely you are to vaporize things. That's not surprising. I think the other thing that a lot of you might recognize is that notice things like alcohol, ethanols, have very, very high vapor pressures, even at low temperature, right? And you guys know this from using things like hand sanitizer, right? You can dump hand sanitizer on your hands, and in less than a minute, it's all gone, right? Because it vaporized. It has a very high vaporization point. Whereas water, right, actually has a low vapor pressure at lower temperatures. You have to heat water up a lot to increase its vapor pressure and actually get it to turn into a gas. Okay. Again, I know it's kind of a tricky concept, but here's another example which hopefully might help clarify things for you. Oh, I think we got one more time to climb thing. Actually, hold on. I might skip this one actually and jump ahead. Let's just do the actual quiz questions because I don't think it's worth the time to get everyone logged in. So here's the actual, can I jump to this slide? Hold on, jump to the end. This should be the right. Okay, is everyone seeing a question on their screen?
Yeah.
Cool, all right, give that a go. This relates more to what we were just chatting about with vapor pressure. Again, think of vapor pressure as a likelihood it will turn into a gas. High vapor pressure turns into a gas very easily and evaporates very easily. Low vapor pressure, it's going to remain in liquid form. You have to apply a lot of heat to get it to vaporize. Try these two questions. All right, looks like we've got answers from most people. I'm going to share the correct results. Hopefully you see what's on the screen, but just to take a look. So the first question was, you're all very experienced with using hand sanitizer, hopefully at this point, and as you know, it vaporizes really quickly off of your hands, and this is because it has a very high vapor pressure. So the correct answer is A, right? Alcohols, if they're exposed to air, will evaporate quite rapidly or vaporize quite rapidly. And with hand sanitizer, if you notice your hand feels cold, and it's the exact idea that I was just talking about with sweating, that as you apply hand sanitizer and it starts to vaporize off of your skin, it's actually absorbing heat and removing it from your skin. That's why it makes you feel cold. So I find that kind of interesting. All right. Last few slides here, and then we can wrap this up. I'm going to have to reposition on this. I don't like that I can't jump to slides. I'm going to have to click through. That's okay. Okay, all right. Last important concept to wrap your minds around here. Bear with me. We need to now give a scientific definition to boiling point, okay? So this is what we've been building up to. The scientific definition of boiling point for water or any other substance is this. It is the temperature at which vapor pressure, remember that's the likelihood that it will become a gas, is equal to air pressure. Which I know is a weird concept, but you have to sort of imagine that every single liquid has a certain vapor pressure, right? There's a certain point of kinetic excitability that if it gets to that, it will vaporize, it will turn into a gas. However, this is always being contradicted by pressure from air, right? You have miles and miles of air on top of your head. We don't notice it because we evolved to live at sea level, but you are under air pressure at all times, and so are liquids. And so the only way that you can get a liquid to jump into the gaseous phase is if you excite those molecules enough, right? And so vapor pressure is just a way of measuring that once you have achieved the point where vapor pressure and air pressure are the same, that's when whatever liquid you have will begin to boil. Again, I know this is a confusing concept and a confusing way to think about things, but just keep that trend in mind and it will hopefully kind of click in time, right? Boiling point is where vapor pressure is equal to air pressure. The important takeaway from this means it's actually air pressure or atmospheric pressure, those are the same thing, atmospheric pressure, that determine the boiling point of substances, right? Most of the measurements we have, like water being boiling at 100 degrees Celsius, is based on the fact that water is at sea level. But you can actually change the atmospheric pressure depending on where you are. If you're actually up at a higher elevation, so again, we all live down here at sea level, right? Where you're actually under a lot of air pressure, but we don't notice it because we're evolved to experience that. But if you were to climb to the top of something like Mount Everest or K2, you have way less air sitting on top of your head. You're experiencing much lower air pressure. And that means that boiling point will actually be a lot lower because if there's, right, you've got vapor pressure has to equal atmospheric pressure at low elevation, that atmospheric pressure is going to be really strong. But at high elevation, it's going to be really, really small. And so you'll actually, it's very easy to achieve the vapor pressure you need to get a liquid to boil. So we'll explore this a little bit. You're going to watch a demonstration of this for your homework as well. So this diagram kind of clarifies things, at least for me. So at sea level, where most of us are right now, you're experiencing about 101.3 kilopascals of air pressure. That's what's sitting on top of you. And so obviously, if you heat water to 70 degrees Celsius, as you all know, that's not the boiling point of water. So notice the water is not boiling. You have to heat it to 100 degrees Celsius, then you start to see the boiling. And again, that's just the point where the vapor pressure now in the water is equal to the atmospheric pressure pressing down, and so it can turn into a gas and escape, right? It is now likely to become a gas. But if you were to go to the top of Mount Everest, so that's not at sea level anymore, look at the atmospheric pressure. It's way lower. See, instead of 101.3, we're at 34. There's much less air pressure, and therefore, even heating water to just 70 degrees Celsius, it boils. You can see the bubbles right there because you have lowered the boiling point. Again, there's less air pressure, and so it doesn't take as much energy to achieve the vapor pressure you need to get things to boil. So just keep that concept in mind. You'll watch a demonstration of this for homework, but I'm able to simulate this in the lab. So in our laboratory here on campus, we have a little like vacuum chamber, as you can see here. And so I place a beaker of water that I heated that water to 80 degrees Celsius, and it didn't boil, right? Because even since it's sea level. But once I insert it into this and I use this machine in the back to vacuum out a lot of the air, it decreases the air pressure, and I can actually get this water to boil at 80 degrees Celsius by decreasing the air pressure on the inside, right? So I bring the atmospheric pressure down so that the vapor pressure of the water at 80 degrees Celsius manages to equal it, and then you'll see it boil. So you'll be doing that for homework. I made a little ed puzzle for that. But this is important for mountain climbers, right? And people who live at high elevation, even living in places like Lake Tahoe or in parts of Nevada, your water is going to boil a lot faster because it doesn't have to get to 100 degrees Celsius. It can get to like 85 degrees Celsius. It actually changes baking rules too. So if you're trying to bake things at higher elevations, you're going to have to cook things either longer or shorter periods of time because the air pressure is different. Okay, one last question to try here. This is giving you the opposite situation. So you visit Prague, which is a city located below sea level, believe it or not. It's technically lower than the ocean. This means atmospheric pressure in Prague is a bit higher than in most other places. Atmospheric pressure is higher. If you wanted to heat some water to a boil in Prague, what would be true about the boiling point? All right, looks like most of you are feeling good. I'm going to share the response right now. But the correct answer is that it would be a little bit higher than 100 degrees Celsius because, again, now you've got more atmospheric pressure. It's greater acting on top. And so the vapor pressure is going to have to be a little higher to match that. So you've got heat to a little bit higher than the normal, higher than 100 degrees Celsius. All right. What'd you think of Nearpod? Meh. Next. I don't know. It's a lot of work and kind of similar results, I think, to what we would normally do with just polls and stuff. So, all right, kids. Homework is to read more. Or no, sorry. The only homework I think is the Ed puzzle that's posted there, and just making sure you've completed the various things we did in class. That is it for me. I'll hang out if you have any questions. Thank you very much. Have a good rest of your day.
Thank you.
Thank you.